State functional analysis. In functional analysis, a state of an operator system is a positive linear functional of norm 1. States in functional analysis generalize the notion of density matrices in quantum mechanics, which represent quantum states, both SSSS mixed states and pure states. Density matrices in turn generalize state vectors, which only represent pure states. For M an operator system, in a C** algebra with identity, the set of all states of M, sometimes denoted by Sm, is convex, weak asterisk closed in the Banach dual space M asterisk. Thus, the set of all states of M with the weak asterisk topology forms a compact Hausdorff space, known as the state space of M. In the C** algebraic formulation of quantum mechanics, states in this previous sense correspond to physical states, i.e. mappings from physical observables self-adjoint elements of the C** algebra, their expected measurement outcome real number. Jordan decomposition. States can be viewed as non-commutative generalizations of probability measures. By Gelfand representation, every commutative C** algebra is of the form Chero X, or some locally compact Hausdorff X. In this case, SA consists of positive radon measures on X, and the SS pure states are the evaluation functionals on X. More generally, the GNS construction shows that every state is, after choosing a suitable representation, a vector state. A bounded linear functional on a C** algebra is said to be self-adjoint if it is real-valued on the self-adjoint elements of a. Self-adjoint functionals are non-commutative analogues of signed measures. The Jordan decomposition in measure theory says that every signed measure can be expressed as the difference of two positive measures supported on disjoint sets. This can be extended to the non-commutative setting. Theorem every self-adjoint f in a asterisk can be written as f equals f plus f, where f plus and f are positive functionals and f equals f plus plus f. It follows from the above decomposition that a asterisk is the linear span of states. Some important classes of states. Pure states. By the Crane-Millman theorem, the state space of M has extreme points. The extreme points of the state space are termed pure states, and other states are known as mixed states. Vector states. For a Hilbert space H and a vector x in H, the equation ox(A) equals x for a in BH defines a positive linear functional on BH. Since oxone equals x2, ox is a state if x equals 1. If A is a C** subalgebra of BH and M an operator system in A, then the restriction of ox to M defines a positive linear functional on M. The states of M that arise in this manner from unit vectors in H are termed vector states of M. Normal states. A state T \displaystyle\tau is called normal if for every monotone increasing net H A \displaystyle H\alpha of operators with least upper bound H \displaystyle H T H A \displaystyle \tau H\alpha converges to T H \displaystyle \tau H . Tracial states. A tracial state is a state T \displaystyle such that T AB equals T BA \displaystyle \tau AB equals \tau BA . For any separable C** algebra, the set of tracial states is a Choquet simplex. Factorial states. A factorial state of a C** algebra is a state such that the commutant of the corresponding GNS representation of it is a factor.